All right, everyone. Good morning. Welcome back to the normal, the land of the normal, where we're doing our Zoom lectures live. Thank you for your patience in dealing with the last week's worth of classes being pre-recorded. I've seen my views uh, increment, so that's good. People are watching this stuff. Remember, you are still responsible for everything from the past week, from the 15th and the 20th. So we talked about due dates for homeworks, we talked about material, all that stuff. So if for some reason you have not watched that, please go back and watch that because we don't have too much time left and you're responsible for the material. So really quickly, just going to talk about some things that some of which we've talked about, some of which we haven't. Homeworks 7.7 and 11.1 both due today, the 22nd. 11.2 is going to be due on the 27th, and 11.3 is going to be due on the 29th. This is the last homework that I will mandate. So the chapter 10 homework, while we will see like one question on the final exam from chapter 10 from the material we cover, I'm not going to require the homework, but I still suggest that you do it. I think that's pretty obvious why, because doing the homework will help you with the one or maybe even two problems from chapter 10 on the final. And it would not be any curveballs. You will have seen the type of problems that we my mind just went blank for a second. Let me try that again. The problems that you would see on the final will be like the ones we see in the lectures today and next class that would come from chapter 10, of course. And that would keep them on the simpler side of things as well, because the stuff from chapter 10 can get pretty complex and wacky, but we're going to avoid that. So what big stuff do we have coming up? Test 3. Test 3, we'd have our dates, the 26th and the 27th. That is Monday and Tuesday of next week, like we previously talked about. So this is a normal test where you've got 2 days to take it. You get one attempt. You are allowed a calculator, no notes or books besides that. If you wanted to use the formula sheet from test 2, you could, but it's not going to do you any good. I can promise you that because it's very different material. And then you'll have to submit your work in Canvas within 15 minutes of completion. You get 2 hours. There's a review available in my math lab that will be very, very comparable to the test itself. So it's going to cover the 4 sections from chapter 7 and the 3 sections from chapter 11. And this will be the one and only instance where there's a section of material that we're going to be finishing today, and it won't be a week until we test on it because I can't give you test 3 and the final on the same day. So that's why we're going to go ahead and knock out test 3 on Monday or Tuesday. But I did warn you that this was very, very likely to happen for the last section. I warned you about this very early in the semester, if not like the first week or two. So hopefully that's not going to be a big deal. It's not like the whole test is on 11.3, just again, normal 1 or 2 problems. So remember, you can email me and ask for partial credit requests, and then I'll let you know how that goes. Please email me. Last time I was able to find some partial credit for a couple people without sending a request because I had a lot of time, but this time that's not really going to be the case. So it is in your best interest to email me. And even if you think, well, is he going to give it to me or not? Take the chance, because what's the worst thing that happens if you ask me? I say no. Just like many things in life, it's not too big a deal to ask. You might get a yes, you might get a no. Hold on a second. Sorry, I had to cough. Okay, so test 3, normal test, 26 and 27. Don't forget to take it. No late work allowed for that. Final exam is going to be 1 day only. That's the 29th because it's a final. We can only give you 1 day, and we will not hold class that day in case you need the class time to take it. We're going to stick to 28 questions for the final exam. I don't know why I said stick to, because we've never had a 28 question test before. We're going to use a 28 question final exam. You will have 3 hours to take it. That is more than enough time. This is regularly a hour and a half test, and I'm just giving you extra time because technology can be wacky sometimes. You are allowed a calculator for this one, but you still need to show all your work. You are allowed to use the formula sheet from test 2, and you will want to use that because some of that stuff can be in the final. The final is cumulative. And there is a review available in my math lab. And I believe the test 3 review and the final exam review are both available. I know test 3 is, and I'm like 99% confident about the final exam review. I think I made that available a week ago at this point, which is why I'm questioning it after having just done my other classes. So with that being said, we are going to pick up where we left off, talking about these sequences and series. We had given the formula for a geometric series last time. So when I pull up the video, I'm just going to leave it paused for like 15 seconds so you can see that in case you haven't before, which you should have, but just in case. And then if you haven't seen it, make sure you go back and check out the last class's video so you can get that basic introduction. But remember, we said an arithmetic sequencer series is where the next term is just the previous term plus a common number, that D, that common difference that we used, whereas a geometric series is where the next number is a common factor or multiplier, which we call R, of the previous one. So that's the difference of arithmetic and geometric sequences and series. I was trying to say sequence first and I said the wrong word. All right, so here we go.
So let's develop it. Now that you've got it written down, and here we go. So I'm just gonna put this on another page. So again, there's your formula. I'll even write it up here just to show what we're trying to achieve. So that's what we're trying to achieve. So here's the proof. And I'm gonna have to pause in a minute, but this will be really quickly. Let's just show what this sequence is. S sub n, which would be A1 plus A2 plus A3 plus A4 plus da 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 A sub n minus 1 plus A sub n. It's just the first of the nth terms. Now, each of these terms is something very specific, though. A1 is A1. A sub 2, we just showed with a previous formula, not the one you see on the screen, but just to find a specific term, is the first term times R raised to 1 less power. So that would be, if this is the second term, that means it's R to the first. And I will be explicit and write that 1 here. Plus, that means the third term would be the first term times R squared. The fourth term would be the first term times R cubed. The da 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 I'll leave alone for a second. I'll give you a second to catch up. All right. But the da 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 da, I want to write these two things over here. So what's the n minus 1 term? Well, it's still a sub 1, the first term, times an r raised to 1 less than the term we're finding. This term is n minus 1. 1 less than n minus 1 is n minus 2. Because negative 1, negative 2. Negative 2 is 1 less than negative 1. Plus the a sub n would be the first term times the r. Well, if that's the nth term, this is definitely n minus 1. All right, so there's S sub n. Now, this is just a trick. This is a trick that some mathematician figured out forever ago. Let's hold on to this thing. I'll do it as a blue asterisk. And now what I'm going to do is I'm going to take the above line and multiply both sides by r. By r. Why are we doing this? Because it just happens to work. How did some mathematician figure this out forever ago? Because they tried 10 billion things and this was the 10 billionth thing that actually worked. That's just how the real world works sometimes. That's how medicine works. They try 10 billion things until you find the thing that works, until you get your vaccine. Lots of failures in between, but we stand on the shoulders of giants and just take the one that works and forget the 10 million others that didn't work. All right, so we're taking R times S sub n. So every single one of these things is going to get an extra R. Every single one of them is going to get an extra R. So A sub 1 times R, because there's an extra R there now, then plus, and actually, let me see if I can do this. It's a pain, but I'll keep what was there before in black and what's new in red. So what was there before was black, what's new is red. So then plus A sub 1 R to the first times R plus A sub 1 R to the second times R plus A sub 1 R to the third times R plus da 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 A sub 1 R to the n minus 2. I said 2, but I wrote 1. There we go. Times R plus A sub 1 R to the n minus 1 times R. Now in blue, I will just show this whole thing condensed. So that's R S sub n equals A1R plus A1R squared, that's R times R, which is R squared, plus A sub 1 R cubed, R squared times R is R cubed, plus A sub 1 R to the 3, 1, 4, plus da 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 da. A sub 1, this is the next to last term, R to the n minus 2 times R. So this counts as an R to the first power. You're adding 1 to this. N minus 2 plus 1 is n minus 1. And plus A sub 1 times R to the n minus 1 times R to the first. Well, negative 1 and 1 cancel, so that's R to the n. Let's put an asterisk next to that thing. Now what we're going to do, this is the final step, well, next to last step arguably, is subtract the two asterisk equations. We're going to treat this like a system of equations. So we're just going to take these two things and subtract them. And admittedly, the order doesn't matter, but I'm going to do the first one minus the second one. So first minus the second. Now, the left side is this thing minus this thing. So again, I'll try and use colors, and this is going to become a pain in the butt, but I'm going to do it. S sub n minus R times S sub n equals. Now I'm going to actually do, how do I want to do this? How do I want to do this? Let's do all the black, then all the blue. So the black A sub 1 plus A sub 1 R plus A sub 1 R squared plus A sub 1 R cubed plus da 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 da. A sub 1 R to the n minus 2 plus A sub 1 times R to the n minus 1. Now I'm going to run out of room, unfortunately. Can I squeeze this? Ooh, that's not what I meant to do. That never works when I want it to work. Okay, forget it. Minus parentheses, I'm just going to put it down here. So then all the blue, A sub 1R minus, I'm sorry, plus A sub 1R squared plus A sub 1R to the third plus a sub 1 r to the fourth plus da 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 a sub 1 r to the n minus 1 plus a sub 1 r to the n. So here's what happens. And again, it's the black thing minus the blue thing. Just pretend that the minus in the blue ink was all over there. These are all minuses. I'm not going to show the distribution because it just gets a little crazy, but that means all of these are negative. So this a sub 1 stays. This a sub 1r has a like term right here. A sub 1r minus a sub 1r. They cancel. This a sub 1r squared has a negative term here that it cancels, minus a sub 1r squared. This a sub 1r cubed minus a sub 1r cubed cancels. That's what that mathematician hundreds of years ago recognized, that if they did this thing, they would have a ton of cancellations. All the da-da-da-da-da's cancel with the da-da-da-da-da. So even though I didn't write a sub 1r to the fourth, that's in there, so it's gone. This a sub 1r to the n minus 2 is the term before this blue one that's in the da-da-da-da-da, so that cancels. This a sub 1 r to the n minus 1 cancels this minus a sub 1 r to the n minus 1. And the only thing you're left with, and this could be infinitely many subtractions, the only thing you're left with is this term and this term, which also has a minus paired with it. So after all that, what we end up with is s sub n minus r s sub n equals a sub 1 minus a sub 1 to the, and then times r to the n. And now our goal here is to solve for s sub n, which we'll have to factor the left-hand side, LHS left-hand side, to do that. There's an s sub n in common, so we take it out. When we take it away from the first term, s sub n divided by s sub n is 1, then minus r s sub n divided by s sub n is r, and then that's equal to the a sub 1 minus a sub 1 r to the n. And then we just divide by the parentheses to solve for s sub n. Divide both sides by 1 minus r. And holy cow, you get the formula. Now you might say, that's not the formula. This was the formula. You had the a sub 1 factored out and with a parentheses. Well, you're right, we did. But that has a common factor, so you can factor it out. 1 minus r to the n over 1 minus r. Q, E, D. Quoterat demonstratum. Proof. Easy, right? Ha ha ha. This is a fascinating proof. I can't tell you how many times this came up in my math degree. How many times this type of thing was used over and over and over. And not always in the same manner, but you have this potentially infinitely many terms, or just a whole bunch of terms, and you need to get rid of most of them somehow. So you take an original thing, you multiply it by an extra thing, and then you subtract the two things to cancel most of the things. So it's a pretty awesome technique. And it's really hard to come up with on your own, but after you've seen it, you get to stand on the shoulders of giants, as we said, and it pushes you in the right direction for a lot of things. But again, what we're really going to be doing is just applying the formula. I don't really have a great way of memorizing this because there's no just logic to it. So let's try it out. Example 2, find the indicated sum. So the sum of the first 5 terms of 4 to the I. Now, I did not tell you it's geometric, so you can't just you can't just use the formula immediately unless you know. Now, after you've done dozens of these, you learn that, spoilers, this is a geometric form, but we need to actually show it by finding the first, second, and third terms, showing there's a common ratio, and then we can apply the formula. But Mr. Beckner, it's only 5 terms. Why don't I just do 4 to the first, 4 to the second, 4 to the third, 4 to the fourth, 4 to the fifth, and add them? Okay, true. But what if that was a 50? What was that, a 500, 5,000? Definitely don't want to do it that way. So first term is 4 to the first, which is 4. The second term is 4 squared, which is 16. Now we're trying to show that they're geometric, which means the ratio between them is always the same. So the so that ratio, 16 divided by 4, the second term divided by the first term is 4. So that should suggest that if this is a geometric, then each term is just 4 times the last term. But is that the r? Well, let's get the third term. 4 cubed is 64, and 64 divided by 16 is 4. Also, the third term is just the first term of 4 times 4 squared, which is 16 times 4, which is 64. So I showed it as the first term times r squared or the second term times r. Those are both the same thing, just a matter of how many r's you're showing. And yeah, you just keep multiplying by 4 because each next term just means the exponent's going up by 1, which means there's an extra 4 multiplier. So that common ratio, that constant ratio, is 4. So you could turn this into a series or sequence where the next term is based on the previous term. So you could say that a sub n is a sub n minus 1 times 4. That would make it recursive. All right, so applying the formula, which I need to zoom out just a touch. The first term times 1 minus r to the n over 1 minus r. If we want to find the sum of the first 5 terms, that's the first term times 1 minus 4 to the 5th over 1 minus 4. Again, cookie cutter, just putting numbers into a formula. That's something you have to practice. The first term was 4, so that's 4 times 1 minus 5 to the 4. I could have gone straight to this. I don't know exactly why I chose to do it this way, and that's something you'll hardly ever hear me say. I don't know why I chose to put the r and the n in, but not the first term. It's fine. All right, 4 to the 5th is some big number. It's 1024. 1 minus 4 is negative 3. 1 minus 1024 is negative 1023. So that's 4 times negative 1023 over negative 3. Obviously, you're going to put that in a calculator. The negatives will cancel, and you'll get 1364. Geometric series can get really large really quick. They can, not always. It depends on the base. The bigger the base, the quicker it gets bigger. If you get a base less than 1, it actually gets smaller each time. We've addressed that marginally before. But it also means that something else could happen that we'll talk about. All right, let's try one more of these. Where's my B? That's weird. All right, well, that's fine. I can just put it over here. I know what it is. I have it in front of me. It's just not on my computer screen. The sum of the first 8 terms of 6 times 3 to the I. Now, again, I'm not telling you this is a geometric 6 times 3 to the I, not 3I. There we go. Big difference there. It wasn't geometric before that. Spoilers, this will be, but we still got to prove it. And that is something I would look for on your work. That I could, if I wanted to, take points off if you didn't establish that it's geometric. Now, you could certainly say, I know this is geometric based on the fact that I've done 100 of these, but I don't really think any of y'all are doing 100 of these before the test. So that's more for moving forward. For now, you need to establish, okay, well, what's the first term? A sub 1 is 6 times 3 to the first, which is 6 times 3, which is 18. The second term would be 6 times 3 to the second, which is 6 times 9, which is 54. If there is a common ratio, it would be the ratio of the second term to the first term. It's an ugly 2, but it is a 2. So that's 54 over 18, which is 3. So if the third term is 3 times the second term, then we're okay. So a sub 3 would be 6 times 3 to the third. 3 cubed is 27. And sorry, I thought I had that written down. 6 times 27 is 162. So if we take 162, oops, that looked weird. A sub 3 divided by a sub 2, it's 162 divided by 54. You get 3. So that's a second way of proving that it's a common ratio. The other way was you find is a sub 3 equal to a sub 1 times r squared, which would be 18 times 3 squared, which is 18 times 9, which, yes, it is most certainly 162. So r is equal to 3. That's our common ratio, our constant ratio, whichever C word you want to use. So the sum of the first 8 terms of this geometric series. And see, when I use this S, is it arithmetic? Is it geometric? I don't know. You have to say somewhere or prove somewhere that it's the R or the D. When I use the letter R, that means it's geometric. If I use the letter D, it means it's arithmetic. But the formula we use is the first term times 1 minus R raised to the 8th all over 1 minus R, where the first term was 18, the R is 3. See, last time I didn't put I put the 3 here instead of an R. That's what I was trying to say earlier. I don't know why I didn't write that last one with R's. I already put the number in. It's arbitrary, but not the end of the world. 3 to the 8th is some big number. It's 6561, so that's 18 times 1 minus 6561. 1 minus 3 is negative 2. So if you subtract 1 and 6561, you're going to get negative 6550. I'm 6560, excuse me. I don't know why I said 50. All over negative 2. The negatives cancel. Half of 18 is 9, so you're just doing 9 times 6560, which ends up being 59,040. It's a pretty large value for just a sum of first 8 terms. But as we said, sequences and series can get large quick. They don't always, as we'll start seeing very shortly. Yeah, we're going to have just enough time to finish. I'll leave that up there for about another 30 seconds, and then we're going to go back to the other page. I think this was an instance where Word, when I was writing my notes, crashed, and it didn't save the last instance. And I just missed the fact that it deleted B, and I kept moving forward when I wrote my notes. It's happened to me a few times. All right. So, actually, I'm missing a whole bunch of stuff. Wait, what? Why is it down here? What happened? Why are those here? All right, it got even weirder than I thought. There's B. My pages are out of order. I don't even know how that happened. All right. Word, everybody. Word is an awesome program. And they don't even pay me to say that sarcastically. So there's B. We'll scroll back up to this in a minute, since I'm assuming it's not going to be down here. And, oh, hey, wait, and there's the proof that I was talking about earlier. I'm sorry, everyone. That's just silly. Okay, doesn't matter. So let's try to find an infinite sum for the first time. This is heavy, heavy calculus right here. Calculus, Calc 2 specifically, you get into all these infinite series, an infinite sum. And specifically, we like infinite series when they're geometric, when there's a constant multiplier. And we can actually find a geometric sum if the constant multiplier in absolute is less than 1. So it can be positive or it can be negative, but it has to be smaller than 1. And this is a very basic idea, because if it's bigger than 1, let's say you just start out with the number 1. Let's say the R is 2. So the next number would be 2, then 4, then 8, then 16. And it would just keep getting bigger and bigger and bigger. Even if your R is 1.01, you'll go to 1.01, then 1.0, whatever. But it will keep getting bigger and bigger and bigger. If your r is less than 1, say like a half, if you start at 1, you multiply and you get a half, then you get a quarter, then you get an eighth, then you get a 16th, then you get a 32nd. You get this asymptotic behavior like we saw back in pre-calc 1 where things start going to 0. So when you require that constant ratio to be less than 1 in absolute, it will make the nth term head towards 0 as you get really, really, really large in your number of terms. It never actually becomes 0. It's going to become 1 millionth or 1 billionth or 1 trillionth or 1 quintillionth, etc., as your n goes to a million or a billion or a trillion, whatever. So it never actually becomes 0, but these numbers, these terms become so, so, so small that it's possible that when you add them all up, you actually get a finite answer. So if your nth term is going to 0, your nth term is basically just some a1 times r to an exponent, and the r to an exponent is going to go to 0 because this is like 0.05 times 0.05 times 0.05 times 0.05 times 0.05. Oops, I should turn my calculator on, shouldn't I? And clear it so we don't get confused. So if you just keep multiplying by 0.05, there's after your first one, here's after your second one, here's after your third one. It's already getting tiny. Negative exponent, tiny. Multiply again. Tinier. Multiply again. Tinier. Multiply again. The more I multiply by a number less than 1, oops, I forgot the times, but you get the idea. It just keeps getting smaller and smaller. So in R, a number raised to an exponent where that base is less than 1 is going to go to 0 as n goes to infinity. This is the type of stuff you really start studying in calculus. Asymptotic behavior, especially trying to get things to go towards 0, or at least a number that's whole, 5, 2, 3, -1, whatever. So what we're going to do is we're going to take that previous formula, so there's nothing new written at the bottom, but now let's imagine that the n is going to infinity and the r is less than 1. So if your r is less than 1, this thing right here is going to go to 0. This right here is going to turn into 0 as your n becomes infinity. As we just said, a number less than 1 in absolute raised to an exponent as you keep multiplying over and over and over and over and over, it just keeps getting more and more and more and more small. It eventually goes to 0. So when you're actually in the infinity state, it literally becomes 0. So that's what we see here. Sorry for the little scribbling there. You can't see most of it anyways. Nothing else changes. The first term doesn't change. The r doesn't change. It's not the r going to 0. It's r to the n going to 0. The r is still just that r, that 0.5 or whatever number it might be. Well, on the top, 1 minus 0 is 1. A sub 1 times 1 is a sub 1. I'm missing a 1 here. Not a big deal. Red, you silly goose. So we can actually find an infinite sum of terms based on this arguably simpler formula. The finite sum is, in my opinion, more complicated than the infinite sum. The infinite sum is just take the first term and divide by 1 minus r. That's it. It's probably the most ironic thing in trigonometry. And this isn't even trigonometry, just in the class where we're taught trigonometry. Math analysis, if you're in high school, is where we learn this usually. So this formula works for a geometric series only, and only if your constant multiplier is less than 1 in absolute. So it can be negative, it can be positive, so you can have an alternating sequence or series, but the multiplier itself in absolute has to be smaller than 1 so that those numbers aren't blowing up over time, either in the positive direction or the negative direction or an alternating fashion. So another formula for you to memorize, arguably easier, but you do have to memorize it. All right, got just enough time to rock these 2 examples and we'll call it a day. Which, that's right, they're up here. And I'll put the formula up here. S sub infinity is the first term over 1 minus r. That's the formula we use as long as constant multiplier, constant ratio is less than 1 in absolute. And Mr. Beckner, you didn't even write this out in a series format. You're right, I didn't. Because quite often they're not. This means you have to establish what the first term is. It means you have to establish what the r is. And that it's less than 1 in absolute, and that you can apply the formula. So 1 plus a third plus a ninth plus a 27th plus an 81st plus a, what's that, 1 over 243 plus yada, yada, yada. And I say go forever and ever. So we keep adding smaller and smaller numbers. So the further we go, the less effect it has on the sum. And believe it or not, you can actually have series where this sum goes forever and the terms are getting smaller, but it diverges. It actually doesn't go to a finite number. It just keeps getting bigger and bigger and bigger. You'll study that in calculus, though. All right. So what's our first term? Well, our first term is very obviously 1. Our first term is 1. What's the second term? Well, it's very obviously 1/3. What's the ratio of these two things? A2, if it's geometric, then the r is the ratio of the A2 to A1, which is a third divided by 1. Anything divided by 1 is itself, so that's a third. Now that's if it's geometric. To prove it's geometric, we take the second term, we multiply it by what we think is the r, and see if we get the next term. And certainly 1/3 times 1/3 is 1/9. So the third term is labeled up here as 1/9. If we take the second term times what we presume is the r, it's a third times a third, which is also 1/9. So it is geometric. Now, since it's geometric and the r is less than 1 in absolute, we can apply the infinite sum formula. If the r was, say, 3 instead of 1/3, this is an infinite sum. It goes to infinity. We keep adding bigger and bigger and bigger numbers. But here we're adding smaller and smaller and smaller numbers, and it happens that we can add these up. So we apply the formula. We take the first term and divide by 1 minus r. The first term was 1. The r is a third, so 1 over 1 minus a third. Oh, man, fractions inside of fractions. Mr. Beckner, I was hoping these never came up again. Yeah, that's the thing about hoping. Doesn't always happen. Told you it never goes away. So I would suggest getting an LCD between all the denominators. The only denominator you see is a 3. So I'm going to multiply everything by 3, as you can see here. Pretend like I didn't cancel those out yet. Pretend like I actually clicked eraser. Word. Go. So 3 times the 1 in the top, 3 times the 1 in the bottom, 3 times 1/3 in the bottom. We do that so that these cancel. There's no more independent fractions. It's just 3 over 3 minus 1. 3 minus 1 in the bottom is 2, so 3 over 2. 3/2, also known as 1.5. I love this problem because look at how small that number is, 1.5. Look at what the first number is, 1. We are already almost at the infinite sum by the first term. If we keep adding these infinitely many numbers, a third plus a ninth plus a 27th, all of that just turns into a half. That first term is the biggest chunk of the sum. If you add the first couple terms, 1 plus 1/3, 1.333. We're only 0.166666 away from the infinite sum by the time we hit the second term. If we add the next term, which is plus 1/9, now we're only 0.55555 away. I'm sorry, 0.05555555 away. We are so freaking close to what it actually represents by the third term of the sequence. And if you remember, at the beginning of this chapter, I had said that in calculus, one of our goals is to turn kooky functions like sine and cosine, which we can't just crunch numbers by hand with, into polynomials, infinite sums of polynomials, but where you really only need the first couple terms of them, because by the time you're at the second or third, most of the time, you're pretty much at what it really represents. Is it that big a deal if we're 0.05 away? It depends on the scenario. And that's where we start getting into error ratio arguments, error propagation, all that stuff. All right. So again, just the point of this is you really, in these infinite sequences and series that converge, by the second or third or maybe fourth terms, you usually pretty much have the approximate value. It's an approximation. It's not exact, but it's approximation. If you use all 10 quintillion of them, then you get it exact. But again, in computational math, what a lot of people like to do is take crazy exponential sine, cosine functions, things you just can't crunch by hand, turn them into just a couple polynomial terms that approximate within a window, and boom, you're good enough to go. All right. Last problem of the section, last problem of the chapter, B. Two minus one plus a half minus a fourth plus an eighth plus yada, 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 yada. So that would be minus 1/16 plus 1/32 minus 1/64 plus 1 over 128. Each of these numbers just keeps halving, but they also change sign, whereas in A, they kept decreasing by a third each time. So B, not only are the values getting smaller in absolute, but they're also alternating. And if they're alternating, that means that the R is negative because you're multiplying by -1/2 each time, spoiler alert. How do we show that we're multiplying by -1/2 each time? You find the first term, you find the second term, you divide them, you find the third term and make sure that it works in that pattern. The first and second terms are already clearly labeled. I did not give you formulas to plug in. I could certainly give you formulas to plug in. I could certainly have made the problem look like this instead, the sum of the first to the infinite term of, what was it, 2 times a half, -1/2 raised to the I. I think that would be the formula. So I could have given it this way, and then you have to plug I equals 1 in to find A1, plug 2 in to find A2, plug 3 in to find A3, do those ratios, et cetera, et cetera. All right, first term is 2, second term is -1, divide them. Make sure you do the second divided by the first. So if it's geometric, then that R would be the second divided by the first, which is -1 divided by 2, which is, well, very obviously -1/2. So if the third term divided by the second term is -1/2, or if the third term is the second term times -1/2, both of those arguments work, then you're good. Well, we can see that the third term is exactly 1/2, +1/2. So is the third term the second term times R? Well, the second term is -1, the R is -1/2. -1 times -1/2 is +1/2. Or you could have done 1/2 divided by -1, which is -1/2. Again, you could just do A3 divided by A2. That's another way of showing the work. So yes, this is geometric, with the R being -1/2 and the first term being 2. And again, me writing out the numbers that way is exactly the same as if I'd written it this way, the sum of the first through the infinite terms of 2 times -1/2 raised to the I. That's the same thing. I plus 1, I minus 1. It's close. Hold on. The first term should be 2, so I minus 1. I just want to fix that. It's actually that. That way, if you plug in 1, the -1/2 will be raised to the 0, and it spits out your 2, and then it just keeps halving each time. All right. So the infinite sum, using that formula, it's the first term divided by 1 minus r. It doesn't have that extra 1 minus r to the n. That's actually the convenience between the finite sum and the infinite sum of geometric sequence and series, because they're very similar. The infinite sum, you just cut out the 1 minus r to the n. I think the infinite sum makes the finite sum easier to remember because you get a twofer, basically. So the first term is 2. The r is negative a half, so you get a double negative situation going on. 1 minus negative a half, which is 2 over 1 plus a half. LCD that bad boy. The only individual denominator we see is this 2. So all the bits get multiplied by 2. Pretend like you don't see the lines crossing out quite yet. There we go. So we're here, 2 times 2, 2 times 1, 2 times a half. These 2's cancel. So you just get 4 in the top. The 2 times the 1 here is this 2. With these 2 canceling, you're left with just the 1. 2 plus 1 is 3, and the answer is 4/3. 4/3 being 1.33333333. 33333. So check this out. Let's just add some of these numbers. And, well, I mean, the first number is 2. 2 is pretty close to 4/3. I mean, it's 0.6 off roughly, 0.66666. So it's in the ballpark. It's not too exact. So I don't know that one term is good enough. All right, well, maybe we just use the first 2 terms, 2 minus 1. That's a little closer to 1.3, but it's still 0.3333 off. So it's good, but it's not great. Well, let's put in the half. So let's add a half. Now we're 1.5. Now, the previous problem, we were slowly gaining to that value. This time we're kind of dancing around it. We're dancing around that 1.33333. We start at 2 on the right, then we're at 1 on the left. Now we're at 1.5 on the right. I bet the next time when we subtract a quarter, we're going to be to the left of 1.333, and we are. But each time, even though we're oscillating, with each oscillation, we're getting closer and closer and closer. So now by the time we get to the first, second, third, fourth term, 1.25 is pretty close to 1.33. Depending on the scenario, maybe it's good enough, or maybe we need the next term. Maybe we need the next 2 terms. But when I add an eighth, now we're only 0.04-ish away. When I subtract the 1/16th, now we're only like 0.02 away. We keep getting closer and closer. We are converging to this value. And again, in terms of applications in computational math, maybe we only need to be within like a 2% error ballpark, and maybe we're in that 2% now. We're actually a little better than 2% in fact. You know, what kind of error is acceptable? 1% error, is that okay? 5% error, is that okay? 0.1% error, is that okay? Depends on the application. All right, so that is chapter 11.
All right. Now, before I start the next video, the longer video for tonight, or tonight, what am I talking about? Today. Tonight. It's 11:50 a.m. and it's tonight apparently. Haha. All right, so before I start the next portion, I need to mention 2 things. First, when I recorded the next portion originally yesterday, I think I've mentioned my technology's been having some issues yesterday, or just in general. Maybe that was to my 154 class, but whatever happened when I recorded my video and I checked the playback, everything was super blurry. I don't know why. I don't know if my internet was struggling. I don't know if my laptop was running like a security scan or something, but I didn't have time to re-record everything. So I'm going to be taking a video from a previous class. I've done it a couple times, but I just wanted to mention, because normally it's only a small chunk. This is an entire section's worth. So this, if you hear me say any dates like April, just ignore them. If anything sounds a little weird, just ignore it. It's the material that matters. So I'm using a much older video than normal to account for when I made our video, it was super blurry. Again, I don't know what happened with my tech. I couldn't fix it. It looked nothing like what you see on the screen. It was readable if you're on a laptop, but I think if you're watching on a cell phone, like a couple of y'all are definitely doing, I expect, I just don't think you would have been able to read anything. So I couldn't handle that quality. So we're going to use an old video. The second part is, and I was wondering whether or not I wanted to do to leave in the error or not. Usually, if I make a mistake, I skip over it. But we're gonna see me make a mistake on graphing something eventually, and I'll point out when we get to the example. It's example one. It's about 50 minutes in. And I'm gonna let it play out so that you can see me being a human being and me correct the mistake. So I will pause once we get to that example, warn you what's going to happen so you know not to necessarily draw the graph. Just follow me. After a couple minutes, I'll realize what has happened. I'll correct it and everything. But that's not going to be for a little bit. So again, I'll warn you when that's coming up. All right, so just give me a minute. All right, so we're going to go back to chapter 10. We're going to get as much of chapter 10 done as we possibly can with the next like class and a half. So let's go ahead and not dilly-dally anymore. So chapter 10, the parts we study at least, I think there might be a 10.4 that doesn't have to deal with this. The chapter 10, the three sections that we study are on what we call conic sections. Now, what I usually do at the beginning of this class is I would go to YouTube and I would pull up a video to help us get a visual aid for conic sections. However, I am going to be posting this on YouTube and I'm going to be recording someone else's content. I'm kind of scared that there's copyright law that I might be infringing, and I don't really want to play with that. So I'm going to suggest that after class, you pull up YouTube and just type in conic sections, maybe demonstration. There might be an extra word to type conic sections or conic sections demonstration or conic sections basic explanation, something like that. And you will get a nice three-dimensional video. One of the first two or three options, the one I always like has a British voice over it, I believe. Or maybe it was a computer voice, a British computer voice, something like that. So I'm just going to give you a very terrible drawing to kind of show you what it goes through instead so that I don't get sued, because everybody wants that, right? I mean, I'm a teacher. It's not like they're going to have any money to take. Ha 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 ha. All right. So here is a two-sided cone. So this is a three-dimensional shape. This is a cone on top of a cone where they're meeting at a point. So this right here is a singular point. That's the top of the bottom cone and the bottom of the top cone. Imagine you just took two ice cream cones, the round, the actual cylindrical cone style, the waffle cone style, that is to say, and you just took their two bottom tips and you touched them so that, you know, if you had ice cream inside of the bottom one, you'd hope that you really jammed it in there so it doesn't fall out and upset your 2-year-old or 3-year-old or whatever. So this is the image that we start with to describe conic sections. And then what we do is we cut this thing with a plane. So we have a two-dimensional flat plane. I don't want to do it that way. And this is really difficult for me to do. And if you were to take this 2D plane versus this 3D cone, if you take that plane and you just kind of cut it horizontally. So in other words, this dotted shape right here, if you were to take your plane, let's say this was a piece of paper and you could just magically slide it through this cone, then the cross section of the cone on top of the plane would be that circle right there. So this dotted shape right here, that's a circle. That is one of the several images that you can get by doing this. Now, this is if we have that 2D plane completely horizontal, completely parallel to the base of the cone. There is another way that you can do this. So I need to draw this image again, and I'm not going to do all of these because I know there's one of them I can't even draw. So the dotted portion is saying that's hidden, it's behind it. We can't technically see that backside of it. I could have drawn that a little more symmetrical, but it is what it is. If you were to take this thing and you were to slice it vertically instead, actually the back one is dotted. And I shouldn't have done it that way. I'm trying to demonstrate that I'm slicing it down the side across the top. The image that you get here, so I'm going to redraw that one. So again, the same demonstration, just from a different angle. So now we're looking at it from the side view. So this is kind of a left view. This will be a side view. So let's take it and do it this way. No. Got it. That's solid. I can make that a little straighter. I told you I didn't really want to have to draw this. But anyways, the shape that you'd have inside here, from where it's intersecting, end up looking like these. They end up looking like parabolas, and that's exactly what they are. So if you slice it horizontally, you get a circle. If you slice it vertically, you get a parabola. If you were to instead, and I'm not even going to try and draw, like I said, this last one appropriately. The video is much better. But if you slice this thing at an angle, the shape that you get inside would be a hyperbola. And I'm not going to, like I said, you really, really, really need to please go and just pull up a video on conic sections demonstrating this. It's going to be able to do a lot better than I can with a crappy drawing tablet, lack of artistic ability, and just, yeah. So again, please, please, please do that. I will say that a hyperbola is going to look very similar to a parabola. So parabolas, you only end up with one or the other when you actually draw them to be functions. That's what we've always seen in the past, but we don't always have to have that necessarily in math. You can have both top and bottom, but we generally don't. The hyperbolas, you always have the top and the bottom. So we know what our circles look like. That's not circular. And then the last one I didn't draw was an ellipse. So we have our circle. And actually, that's not a hyperbola. This is supposed to be the ellipse. Sorry, I'm getting so focused. This is not a hyperbola. This is an ellipse, obviously. The hyperbola is when you go through at a less angle. It's still if you do it at an angle, but it's if you go at a smaller vertical angle. So if I were to slice it like this, that's how you get the hyperbolas. This is an ellipse. So what's an ellipse? Well, this is a circle. An ellipse is just a circle that's been stretched out. A parabola, we all know that shape. But then a hyperbola kind of looks similar, but they're a little wider generally. And they do have a top and a bottom. Hyperbolas are not necessarily functions. So hyperbola kind of sounds like the word hyperbole, which is to exaggerate, and they honestly have nothing to do with each other. Just like a parabole has nothing to do with a parabola. Gotta love math people, right? But these are the four shapes that come out of your conic section. So I demonstrated the circle, the ellipse, the parabola. I did not demonstrate the hyperbola. I meant to show you what the hyperbola should look like, but my bad drawing, and I didn't even think about it, ended up giving the cutout for an ellipse. So I can actually do this one. Just looks like a wider circle. And I didn't draw that further enough over. It should be like that. There we go. Should be touching the edge of it. There we go. There's our ellipse. Not a hyperbola because we did not slice it the correct way. I said the reason if you slice it vertically, you would go through, not vertically, more vertically, you'd go through two sections of the cone, which is why you end up with the two images. So am I ever going to have you testing or questions on any of this stuff? Absolutely not. This is just a demonstration of where these shapes come from. Now, you've dealt with circles before in math classes. You've definitely dealt with them in Math 161. You've dealt with parabolas in math classes. You definitely dealt with them in Math 161. You've probably seen ellipses, but you may not have seen their equations. And I would actually be surprised if more than 10 or 15% of you have dealt with hyperbolas before, unless you've actually gone through this course or gone through calculus. Hyperbolas are something that, what's the phrase I want to use? I don't know how PC that phrase is. It's not rude or anything. I just don't know if I want to say it on recording. It'd be fine in class, but so you don't see these as much in an introductory calculus class. But what's fascinating is they become extremely relevant in higher calculus and things like partial differential equations and other side topics, numerical analysis. And in fact, you can actually combine the idea of a hyperbola with trigonometric functions, and you get a hyperbolic sine and a hyperbolic cosine and a hyperbolic tangent. And they behave similar, but quite different. So they have features of a hyperbola, they have features of a sine, but they don't have every feature of both of those classifications. That tends to happen when you mix and match things. So this is just that bare introduction showing you where these shapes come from. It's all based on how you would slice this three-dimensional image with a two-dimensional image. So let's get into the first official section, 10.1, the ellipse. Okay, so an ellipse, oops, is the set of all points in a plane whose sum of the distances to the two fixed points is constant. And I'm going to all caps that word. An ellipse, we have to think about this for a second. This kind of sounds weird, right? An ellipse is the set of all points in a plane, so that means a two-dimensional shape, whose sum of the distances to the two fixed points is a constant. To two fixed points. There shouldn't be a the there. Sorry about that. I mean, they are specific, the two fixed points. but it doesn't make sense until we explain what they are. So an ellipse is a set of all points in a plane whose sum of the distance to two fixed points is constant. So let's draw an ellipse, and they don't have to be like this. They don't have to be wider, they can be taller, and we will see instances of both. So an ellipse is the set of all points in a plane, so this kind of circular-ish but elongated shape, whose sum of the distances to two fixed points is constant. So we got a fixed point, maybe about here, and a fixed point maybe about here. I'm going to label them F1 and F2 for now. I call them Fs for the first letter of the word they're associated with. And then we have any point on the circle P. So it doesn't have to be this point right here. It could be over here on the far right. It could be the very bottom center. It could be the top left-ish area. This P represents every single point on the ellipse. So we have the distance from this point to F1. That was a terrible looking line. Let me start from here and go up. I tend to be better going left to right. So this would be D1, the distance to F1. This point right here, this distance right here from P to F2, let's call that D2. No matter where you are on the ellipse, D1 plus D2 is constant. It never changes. So if you're on this point, let's say D1 was 7 and D2 is 3. That would add to 10. That means if you were on this point over here on the far right, then if you don't know the distances, you can at least say that their sum is 10. So maybe you know the distance from F2 to the right is 2. That means the distance from F1 to the right would have to be 8 because 2 plus 8 is 10. Or maybe you're here, right dead center. The distance from F1 to the center would have to be 5. The distance from that bottom center point to F2 would have to be 5 in order to add to 10 because it'd have to be symmetrical. That is the geometrically built ellipse. You can also build ellipses algebraically, but this chapter is dedicated to the geometric experience. So I said earlier that you should have all studied parabolas previously back in Pre-Calc 1 extensively. You learn about their vertices, you learn about maxes and mins, you learn about how to graph them using their intercepts, their x-intercepts, their y-intercepts. You learn how to put them in two different forms. There's actually a third form. It's not in this section, but we'll get to it. And it looks very, very different than what you're probably used to. All right. So now that we know the idea behind an ellipse, let's actually show what the equation for it is. And we're not going to derive the equations in this section. That would be extremely time consuming. So if the major, which we'll call the longer axis, is horizontal, let me underline that. And centered at the origin, the equation is, and we're going to go x squared over a squared plus y squared over b squared equals 1. Then there's a little side equation that c squared is equal to a squared minus b squared. So I'm going to have some typing after this to explain what the a, b, and c are. A is the distance to the vertex on the major axis. B is the distance to the edge along the minor axis. That's a lowercase a, not a capital A. Thank you, Word. So what are the A and the B? Let me get a different color to represent up here. A is the distance to the vertex on the major axis. The vertex is the far left and right points in the way we've drawn this up here. These are the vertices. That's the plural of vertex. So this would be V2 and V1, V for vertex. Now, the top and the bottom, we don't really like to call those vertices. That's why I said to the distance to the edge along the minor axis. So in this image, the major axis is horizontal. And the minor axis is vertical. Major, longer, minor, smaller. Pretty easy to remember. So again, A is the distance to the vertex on the major axis. So what color do we want? Let's go with orange. From here, from the center to the vertex, that distance is A. That length is A. From the center to the top or bottom, that distance is B. And again, it works if you draw that down or left. That would be A, going left from the center. This would be B, going down from the center. But what exactly is C? C, lowercase c, thank you word, is used to locate the foci. That's the plural of focus. Well, guess what? We labeled some points F1 and F2 for a reason earlier. Those are the foci, focus 1, focus 2. So the foci are related to the whole geometric build of this, that those distances are constant. Now, we don't get to see D1 and D2. They're different for every single point. The only time we would ever get to see D1 and D2 is a special case, and I don't want to mention it right now. So if we are centered at the origin, if this point is 0, 0, if we're at the origin, so that we can actually use this equation, then the vertices, since we're going left and right A, they would be, actually I'm going to type it down here. The vertices are at negative A, comma 0, and A, comma 0, because we're going left or right by the A. The foci are at negative C, comma 0, and C, comma 0. Copyright. I feel like that's kind of funny since I mentioned that earlier. So C is used to locate the foci. That's the distance from the center to the focal point, one of the two focal points. So again, I'm not saying this distance right here is A, this distance right here is C. What color haven't we used? Gray, dark gray. So I'm going to do it on the left side. This distance right here is C. I know it's a lot of things up there all at once. The D1 and the D2 we will never use moving forward. We just use that concept to build an ellipse. So what's really cool is, and if this was like an elementary class, or even I've seen some high school classes do this, what you can do is you can draw an elliptical shape and you can measure a distance from here to here, and you can poke holes in the focal points, and then you can put pins and you take a string and you make the string taut. And then if you have your pen holding down the string, as long as you trace your pen with the string taut, you end up making an ellipse. So again, you just anchor a string down on 2 points, some distance apart from each other. Then you take your pen, you pull it up so that the string is tight, and then you just start rotating it around clockwise or counterclockwise, keeping it tight, and you end up drawing this shape. Because the length of your string, sorry, I blanked for a second, I had rope in my head. The length of your string is constant, you can't change it. So this was all if the major axis is vertical. If the major axis, I'm sorry, horizontal. If the major axis is horizontal, then you have this setup. So A is going to be the larger number. A has to be bigger than B. A has to be bigger than B in this case. But what about if the major axis is vertical instead? That thing I just accidentally said a minute ago. So I'm not going to show every single detail of this same image. I'll show what's important. So here's a vertical ellipse. Let's see, we did green and orange. So we'll do orange for the longer one. So that distance would be A. I'm not that worried about the colors being consistent. This distance would be B. We still have our focal points. Maybe about here, F1, and here, F2. And the distance, come on, give me my other color. From the center to a focal point is C. Now our major axis is vertical. Making the minor axis horizontal. Again, major means the longer. And what I'm trying to demonstrate here is that no matter what, A is supposed to be the longer number. Now, I will admit, in the whole picture, it doesn't matter what you're calling A, B, and C. Those letters are arbitrary. We just like to have them specifically for consistency and setting up examples and everything. But with ellipses, we like A to be associated with the longer side. We like B to be the shorter side. So if, I don't want to do that. If the major axis is vertical, like in this left image, and centered at the origin, the equation is, let's get our black. We're going to have x squared over, now it's b squared, plus y squared over a squared equals 1, where the c squared is the same thing. The only thing that's changed is we swapped the a's and the b's, and honestly, it really doesn't matter what you call them. You could still have this as x squared over a squared plus y squared over b squared, as long as you had the a and the b swapped in the graph. All we are associating is that the bigger number tells you which axis is longer. So if the number under the x squared is bigger, that means that the major axis is horizontal. If the number under the y squared is bigger, that means the major axis is vertical. So the numbers under the x's or the y's are just the square of the distance either in that direction to the edge of the ellipse. So these are your forms for your ellipses that you have to understand and practice. The c squared aspect is also important. I'm only going to highlight it in one of them. It's the same thing in the other. This is extremely similar to a circle. A circle is x squared plus y squared equals r squared when you're centered at the origin. What's the major difference here? Well, you have a horizontal radius and you have a vertical radius, basically. So that's why we have different radii for the x and the y. So it can't just be a single r squared. So basically this divides by that quote r squared, but now allows them to be different numbers. So if this was a circle, the a squared and the b squared would be the same. You could multiply both sides by that common denominator, just call the a and the b r. So both bottoms are r squared. You multiply both sides by r squared and you get the equation of a circle. So we don't really focus on circles in here because all the circle arguments are the same as what you've seen in previous classes. We focus on the ellipse, the hyperbola, and the parabola, but the parabola done quite differently. And we may not get to all of that like we've said, but we're going to do what we can. All right, so let's try this out finally. Example 1. Identify A, B, and C, the important components of the ellipse, and then graph it. And for A, we're going to have x squared over 49 plus y squared over 36, I believe. Yes, equals 1. So we were given the equation for the ellipse. This is not a function. Doesn't matter. Not everything in the world has to be a function. These definitely fail the function test. They fail the vertical line test. They're also not invertible because they're not a function. Even if they were a function, they would fail the horizontal line test. But again, not the point. So we just need to look at this and say, oh, okay, well, the x squared has the bigger number on the bottom. So that means that this thing is going to open up horizontally. Remember, we said the bigger number tells you which one is wider. So that says that the x has a wider range, and it relates to the 49. So you might even want to make just a note up front that this would be a major axis is horizontal case, because the number under x squared is bigger. It has to be wider than taller. So we like to call the a the bigger of the two. So the a squared is the 49. A squared has to be 49 because we're up on this one. If this was vertical, we'd be calling that the b squared, but it's not because 49 is bigger than 36. Well, how do we solve that? You might say take the plus or minus square root, and arguably that's true in an algebra sense, but we're dealing with geometry. You can't have negative links of a negative radius for a circle or an ellipse. So we just take a normal square root. So square root of a squared equals the square root of 49. That tells us that a is equal to 7. So the horizontal radius is 7. I'm not saying the horizontal length of the ellipse is 7 because you actually double it. It would be 14 wide. From center to end, it's 7. So that's our a squared. How do we get the b squared? Well, that relates to the number under the y. So b squared would be the 36. Take the square root of both sides. Again, no plus or minus needed. We've got to skip that a lot in this course, but not always, which tells us that b is equal to 6. So that tells us the vertical length from center to the edge of the ellipse. So it's from the center going left or right, that's a 7 distance. From the center going up or down, that's a distance of 6. Once you have A and B, you can find C using that formula. It's the same formula whether it opens vertically or horizontally. I don't want to say opens vertically, whether it's wider or taller. So C squared is A squared minus B squared. So that's 7 squared minus 6 squared, which is 49 minus 36, which is 13. So we know that C squared is 13, so we take the square root of both sides, telling us that C is equal to the square root of 13. Those are the A, B, and C. Now, I don't have to give you the equation and ask for the information. I can give you the information and ask for the equation. I can give you the A and B, and then you can build your equation. I could also give you the A and the C, and you can build your equation. Or I can give you the B and the C, and you can build the equation, because we know how to algebraically rearrange things. I can give you C and A, excuse me, and then you can solve for B. I can give you B and C, and you can solve for A. C is important for the focus. C is important for the focus. A and B are important for drawing the ellipse itself. So again, we got a vertical distance of 7, a horizontal distance of 6, and then this square root of 13 will relate to the focus. So let's start drawing this thing. So here's our axes. We're centered at the origin. We're going to go up 7. 1, 2, 3, 4, 5, 6, 7. We're going to go down 7. 1. Coming at you live for a second. So I had put that little warning on the screen that this is where the mistake was going to be when it came to the graph. And here is the mistake. You'll notice I said we're going to go up and down 7, but A was 7 and A was under the X. See the 49, that's our 7 squared, which says I should have gone left and right 7. So again, I'm just going to let this play out, and then you'll see me catch the mistake, and then I'll correct it. But again, this is what happened. And again, I'm reminding us that we're all human, but that we can catch our mistakes as long as we're paying attention to the details. I was just rushing. I was writing and talking and thinking at 3 different speeds. So I just swapped the A and the B in my head, unfortunately. So again, this should be a 6. We will get the correct graph in a couple of minutes, but for now, let's let the mistake play out. 2, 3, 4, 5, 6, 7. We're going to go left and right 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And those will be the points of our vertices, which are the top and bottom, and then just the outer points along the minor axis. Some people will call them vertices. It's kind of a misconception to do that. I wouldn't care. I may or may not have called them, just minor vertices. I kind of like calling them that, but it's an unofficial name. And then you just make a circular-like shape formed out of those points, but not exactly a circle. It will be a little stretched in one direction. Come on, Rodney, you can do it. You can do it. Oh, that was going to be bad. Not too terrible, not too terrible. So there's our ellipse. But that is not all we want. When we're drawing our ellipse, we want to describe the foci as well, the focal points, those 2 points that if you anchored a string with, you could actually draw the ellipse if you had that string the appropriate length. So the focal points relate to the C. So let's just go and label our vertices. So the vertices, that was the 0, 7, that's the top point, and 0, -7. Now you might say, well, hold on, Mr. Beckner, back up here, you said the vertices were at the plus or minus, or the A goes in the first spot. That was for the horizontal. I didn't actually write all this out for the vertical one. Because when you go the other way, you swap X and Y coordinates. The foci and vertices are always along the major axis. So if it opens horizontally, those are always an X value, which is why it's always -A, 0 or A, 0 or -C, 0, C, 0. If we're opening vertically, that means the change is along the y-axis, so the A and C values have to be in the y values. I think it's very important to understand this idea because sometimes you're asked to type out these points, not just graph them. So the vertices, that was the up and down 7. Oh no, look what happened to my shape. That's silly. If I hit enter enough, will it fix it? Yes, it will. Okay. I want to do it here though. There we go. Okay, back to the problem. So we said our vertices are the top and bottom points, the ones along the major axis. The foci, again, have to be along that same axis. So it has to be 0, something and 0, something. Well, the something is the plus or minus of the C. So one of them is at 0, square root of 13. One of them is at 0, negative square root of 13. Where exactly is square root of 13 up here? Well, square root of 9 is 3, square root of 16 is 4, so it's somewhere between 3 and 4. If you want a better approximation, then you can pull out a calculator. My eyes are crossing. Where's my square root button? Is it not up there? That's weird that it wasn't on that one, or I just wasn't seeing it. All right, so square root of 13. I gotta type the 13 first in this one. 13 square root 3.6. So 3.5 would be good for graphing. So if this is 1, 2, 3, if this is 4, it would be halfway between that. So let me do that in a different color for emphasis. We'll do it in blue. So here at about 3.5 roughly, and then down here at about -3.5, those points would be 0 comma square root of 13 and 0 comma negative square root of 13. So again, square root of 13 is about 3.6. I think I saw, yep, someone's got a question. A is based on yes, Jared, you are correct. I am so sorry. It's been a really weird morning. Ah. I even said it was horizontal up here, and then for some reason I just swapped these numbers. All right, so what all do we have correct? We said the major axis was horizontal. We got our A's and B's right. We got our C's right. The only thing I did wrong is I drew it vertically instead of horizontally. So I need to erase the image. I'm really sorry about that. Erase, erase, erase. And all of these are swapped. Let's try again. -5 for your teacher. All right, so shortcut, -7, +7, 6, -6. This should be wider than it is taller because it opens, and that opens, that's a bad habit I have of saying it opens horizontally. It's wider than it is taller. That's what it should look like. And then at about 3.5, so if this is 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 2, 3.5, 1, 2, 3.5. So our vertices were at 7, 0 and -7, 0. Our foci were at square root of 13, 0 and negative square root of 13, 0, where at least the square root of 13 is still 3.6. My bad. My bad. I'm very, very sorry for that. And the best part is it's recorded, so I get to laugh at that later. All right. I'm trying to decide. I actually want to make a memo about that because that was such a more significant mistake. I want to make a memo on the YouTube notes for that. So I'm writing something down to remind myself. Give me a hot second. Okay. So let's just rediscuss this problem to make sure we're all on the same page due to my mistake. We had the x squared over 49, which meant it was going to be wider because 49 is bigger than 36. We did the A's and the B's right. We did the C right. We just drew it vertically on accident because our teacher wasn't paying attention. He was probably doing too many things at once. And then that caused your teacher to mislabel the vertices and foci based on the image. So we erased that. We drew it horizontally like it should be, meaning that the vertices are the left and the right points. The foci should be moving left and right as well. And again, the foci are if you had your string, you anchored it on those points. If the string was the appropriate length, then you made it taut. You could end up drawing the ellipse without even trying. All right, so now that we butchered that, let's try another one, and let's not make mistakes this time. B. And we're going to do x squared over 4 plus y squared over 9 is equal to 1. So this is the format of an ellipse. Now, you know what's funny? If I change this plus to a minus, it's not an ellipse anymore. Just a subtle little detail change like that makes this not an ellipse. It makes it something different that we might get to study if we manage to finish everything in time. I'm probably just going to do kind of a quicker summary next class. I'm going to skip the more complicated problems where we're not centered at the origin. It changes things quite dynamically. And they're fascinating problems. They're very, very useful. But I just want to get the bare essentials in terms of the topic. So the y squared has the bigger number, which means this is going to open vertically, and we'll make sure to draw this one opening vertically. And when I say open vertically, I mean it's taller than it is wider. That open is kind of a misconception. All right, so that means we will call the a squared 9 because this opens, again, that opens. It will be taller than it will be wider, which so we say the major axis is vertical. If a squared is 9, you take the square root of both sides, which tells us a is equal to 3. If b squared is 4, take the square root of both sides. That tells us that b is equal to 2. C squared is the difference of the squares. It kind of feels like Pythagorean, but it's a minus instead of a plus. So we go a squared minus b squared. That's 3 squared minus 2 squared. Some people skip writing it this way because you already know what the squared numbers are, 9 and 4. That's perfectly fine. Just 5. So c squared is 5. Take the square root of both. So c is equal to the square root of 5. So we got the a, b, and c. That means we can graph it, we can draw it, we can identify the vertices and the foci. We don't need to label those outer points along the minor axis. We don't really have a special name for them, so that's why they don't get labeled. Yes, you have to plot them to make the ellipse, but you don't give them a name and you don't write them in detail to the side. So we're going to make this, the major axis is vertical. The y squared number is bigger, so we make sure that this ends up taller. 1, 2, 3. 1, 2. 1, 2, 3. 1, 2. So we got the vertices at the top and bottom. That's the 3 and the negative 3. We have the vertices along the minor axis, if you will. Again, no official point, but that's just kind of what I always called them. There we go. And then you connect them in a circular-like shape, but elongated, so it's elliptical. So there's our ellipse. Because it's taller than it is wider, the foci should be along the vertical part. C, we said was square root of 5. Well, the square root of 4 is 2, so it should be pretty close to that. Let's pull up our calculator. I must have closed it. That's all right. So we're going to do 5 square root, 2.2, so about 2 1/4. I'm going to have a really hard time, getting that exactly right. So we just do our best. Not halfway, maybe about here. So that would be one of the foci. And then down 2 1/4 about here, that would be the other foci. So our vertices, that's along the major axis, that's the ones involving the 3 and the negative 3. Those are 0, 3 and 0, negative 3. The order of the plus and the minus don't matter, as long as you have 0, The foci are 0, square root of 5 and 0, negative square root of 5. And there we go. No mistakes in this one, I promise. So how do we know it's wider? Because the number under the x squared is bigger. How do we know it's taller? Because the number under the y squared is bigger. We tend to call the a the bigger number. Is it mandatory? No. It just changes. The c squared would then be b squared minus a squared if the b was bigger. In fact, because of the squaring, you could argue it doesn't matter, but it would end up, you might end up having an imaginary number somewhere if you do them backwards. And by might, I mean you definitely would if you're paying attention. All right, I'm not going to be able to fit another one here. So let's do C here. Probably our last example for the day. We did that one. We did that one. Let's go x squared. No. 25x squared plus 16y squared equals 400. I was about to forget my 25. And you go, well, what is this? You said these things had to be x squared over a number squared plus b squared over a number squared equals 1. I don't see any denominators, and that right side is definitely not a 1. This isn't an ellipse. You're crazy, right? Wrong. Well, I mean, I'm crazy, but this is an ellipse. But it doesn't look like it. So we need to rearrange things to make this look like it. Now, the main issue with an ellipse is that the variable terms are positive and on the same side, and that the other side is just a 1. We can make this a 1. Now, you might say, we'll subtract 399 on both sides. Okay, but then you got a minus 399 on the other side, and these numbers in front of the x squared and the y squared, that just doesn't seem to fly. So instead of trying to move this by subtraction, let's try and move it by division. So let's divide both sides, aka all terms, by 400. This is a very common technique. So we'll divide this by 400. We'll divide this by 400. Whatever I do to the left side, I'm doing the right side. And with division, you'd have to do it to all terms. And then the cool thing is all of these fractions are reducible now. 25 and 400 are going to reduce. 400 divided by 25 is 16. So this becomes x squared over 16. That looks a little more familiar. 400 will divide 16 perfectly, and it's 25. 400 divided by 16 is 25. I'll leave you to prove that if you need to see it. So those fractions reduce the tops completely, but the bottoms are 16 and 25 equals, and I hope you know 400 divided by 400 is 1. That was the whole point. Boom, we have the form of an ellipse. And now we can tell whether it's wider or taller. The y squared has the bigger number, so that says that the major axis is vertical. It will be taller than wider. So we'll call the a squared the 25. Taking the square root of both of those, you get a equals 5. I think I can skip showing that work a little bit. The b squared would be the 16. Take the square root of both sides, and you'll get that b is 4. The c squared, that's the difference of the squares of the numbers. So that's the difference of the 25 and the 16. That's the a squared minus the b squared, which is 9. So c squared equals 9, take the square root, and you get c equals 3. So there's our a, b, and c. We need the a and the b to draw the image. We need the c to locate the foci. Now you can go ahead and identify the vertices and the foci before drawing it, but honestly, as long as you draw it right, I think it's easier to draw it than identify which one's the 0 in those coordinates. But if you draw it wrong, like a teacher may have done earlier, then you would mislabel them. So you do have to be careful. All right, so again, we're taller. The y has the 5, the x has the 4. I am super paranoid about messing that up now, more so than ever. I'll probably never do it again in my life. So up, 1, 2, 3, 4, 5. Down, 1, 2, 3, 4, 5. Left and right 4. 1, 2, 3, 4. 1, 2, 3, 4. That's the location of the outer points. And then we go like this. As best as your teacher can do. Good thing is my math lab can draw them perfectly. And there's our shape. But we also need the foci, which the C was 3, so that means we're going up and down 3. Remember, the foci are always located along the major axis. So that's the focal points, the foci. So our vertices, that's the numbers along the major axis. That's the 5s, and we're going up and down, so that's 0, 5, and 0, -5. The foci, still 0, but now it's the 3. And there we go. This is definitely not the extent of the section, but this is probably where I'm going to cut it. I think I would rather give a briefer summary of these 3 sections than do one section in complete, but not the other 2. I just don't feel like that's a good idea because we only have really one more class to lecture. Monday is our last lecture. Can you believe that? And I will be lecturing since the reviews are all digital and everything. So again, on next class, we'll really quickly kind of talk about the hyperbola and the parabola. The test questions on the final exam involving this would be no more difficult than what we've done in the class. If you go to the homework problems, those are going to be above and beyond. I really don't even want to say this. I'm going to exempt chapter 10 homework from your grade. I don't want to have to remove all of the problems that should really be in there and just give you the 2 or 3 simple ones. So find the simple ones, make sure you understand how to do them, the ones that were like these 3 examples. You don't have to do any of the rest. If you really want to go above and beyond, you can try and study it on your own. But these things don't have to be centered at the origin. You can have a center here, and then your ellipse, if it opens, I keep saying that. Again, bad habit of mine. If it has a major axis that's horizontal, it would look like this. So then these points, the foci and the vertices, I said them backwards, but that was unintentional, the vertices and foci, they're not just the values of A and C. They're going to have shifts involved, which again, just complicates things a little bit. And you can be given equations that are not necessarily in the appropriate format, and you have to complete the square to get them in the appropriate format. So these problems can become much more challenging, but again, in terms of what will be on the final, I'm not going to do any of the complicated ones. They'll be like example 1, A, B, or C for an ellipse, and anything hyperbola or parabola, again, very simple. I'm not going to give you a lot. I mean, I'm thinking 1, maybe 2 questions on the final involving this. Again, I will exempt the homework. I will not include chapter 10 homework in your grade. So like I had said at the beginning, or maybe it was in the middle. Maybe I said it both times, but chapter 10 homework is available, but gonna exempt it, gonna not actually count it as part of your grade, but it will definitely help you for the 1 or 2 questions that could be on the final. So for the last minute of class, just pulling the whiteboard back up for our due dates. 7/7 and 11/1 through 11/3 all have due dates, some sooner than later. Test 3 is going to be Monday and Tuesday, so hopefully we are prepared for that. The review is available in my math lab. 20 questions, 120 minutes per usual. Calculator is allowed this time. That's the unusual. You are allowed a calculator this time, but I do still suggest that you show all of your work, because if you give me an answer in my math lab on your test and it's a decimal value or something, and then I go to look for work and there's no work, I can't do anything for partial credit if you ask for anything. But if you had showed some work, you showed how you arrived at that calculation, then maybe I can find you 2 or 3 or 4 points. So again, even though you're allowed calculators, still show every bit of work that you can, because that's how you'll get partial credit on something. Besides that, I hope there's no confusions. Thank you for your patience with the mistake I made. Again, I just thought that it would be interesting to leave that in. Um, like I said, I usually cut them out, but that one I just felt I would show that we're all human and everything. So, final exam, the 29th, no class that day. So when we meet on Tuesday, that will be our last Zoom meeting. Per usual, if you have any questions, shoot me an email. Get that homework done, start studying for the tests, make sure you show your work, have your calculators ready, all that good stuff. And we'll see you on Tuesday. Take care, everybody.